Every star in the night sky is a distant whisper, a cosmic mystery begging to be measured. For millennia, humanity has dreamt of charting these celestial distances, of grasping the true scale of the universe. Tonight we reveal the peculiar unit that underpins modern astronomy. It's a story of precision paradox and the unexpected geometry that defines our understanding of the cosmos' breathtaking scale. If you enjoy these explorations, a like or subscribe helps. Now let's begin. Imagine yourself an astronomer in 1837. You stand hunched over your telescope night after night, the chill air biting at your face, your gaze fixed on a faint star known as 61 Cygni. You know with certainty now that Earth is a tiny blue marble hurtling through space, locked in a magnificent orbital dance around the Sun. And you grasp the profound implication: if you possess enough patience, enough precision, and an almost superhuman dedication to careful observation, you might just detect an infinitesimal shift in that star's position against the backdrop of far more distant, seemingly unmoving stars. If you could measure that subtle celestial sway, you would achieve what humanity had yearned for 2 millennia, the distance to a star. Friedrich Wilhelm Bessel, a German astronomer, did exactly that. What he couldn't have foreseen was that his singular measurement would not only shatter ancient cosmic illusions, but would also establish a unit of distance that still dominates astronomy nearly 2 centuries later. It's a unit that makes little intuitive sense to anyone outside the field, a peculiar marker that defines no natural boundary in the sprawling expanse of space, but is based purely on the ingenious geometry of his measurement technique. This unit is the parsec. For most of human history, stellar distances remained an impenetrable mystery, the ultimate cosmic unknown. The ancient Greek astronomer Hipparchus, around 130 BCE, meticulously catalogued over 1,000 stars, mapping their positions, tracking their apparent movements, and recording their brightness. But distance. That was a bridge too far, a question beyond the reach of his era. His best guess, a testament to logical deduction based on available evidence, was that stars resided on a crystal sphere beyond the planets, all equidistant from Earth. This wasn't a failure of intellect or imagination. It was the most elegant explanation that fit the observations of a seemingly immutable firmament. The stars truly appeared as fixed points of light, never moving relative to each other, maintaining their perfect celestial formation night after night, year after year, century after century. The ancient Greeks even coined a word for this celestial sphere, the firmament, derived from the Latin firmare, meaning to make firm or strengthen. The idea was not merely poetic, it was a literal belief that stars were embedded in a solid crystalline sphere rotating around a stationary Earth once per day. This crystalline shell sat far beyond the planets, Mars, Jupiter, Saturn, which the Greeks knew moved tracing complex wandering paths against the seemingly frozen stellar background. But the stars themselves never budged relative to each other. Aristotle in the 4th century BCE further solidified this model by arguing that this celestial sphere must be made of a 5th element, distinct from the earth, water, air and fire found below the moon. He called it ether, or quintessence, a substance inherently perfect, unchanging and eternal. The stars embedded within this pristine sphere partook of its perfection. They never dimmed, never flared, never vanished, moving only in their grand daily rotation with the sphere itself. This comprehensive model held sway for 2 millennia, because nobody possessed instruments capable of detecting the minuscule shifts known as stellar parallax or proper motion. Every single observation, every star catalogue from Hipparchus to Ptolemy in 150 CE reinforced this geocentric fixed star universe. The constellations hadn't changed shape at all. For 2 millennia, the scale of the universe remained a profound enigma. The technology simply didn't exist to peer beyond the illusion of a static sky. Then came the 17th century and the invention of the telescope. Galileo Galilei turned his crude spyglass skyward, revealing breathtaking details: mountains on the moon, Jupiter's orbiting moons, and the Milky Way as a countless swarm of individual stars. Yet even with this revolutionary instrument, the fundamental question of stellar distance remained unanswered. The stars still appeared absolutely fixed. To triangulate an object's distance, you need to observe it from two different positions and measure how its apparent position changes. This is the principle of parallax, the same way your brain perceives depth, using the slightly different views from your two eyes. Close one eye and your depth perception falters. For stars, however, our human baseline of 6 centimeters was ludicrously inadequate. We needed a baseline on a cosmic scale. By the 1600s, scientists had conceptualized a brilliant idea to use Earth's vast orbit around the Sun as the baseline for this cosmic triangulation. Johannes Kepler had already established Earth's elliptical path. By the mid-17th century, astronomers had even measured Earth's orbital size with increasing accuracy, often by observing transits of Venus across the Sun's face. They knew Earth orbits in a path roughly 300 million kilometers in diameter, 186 million miles. This means that in January Earth is on one side of the Sun, and 6 months later in July it's on the complete opposite side. If you observe a star in January noting its precise position against the background of more distant stars, then observe the same star in July, you are effectively viewing it from two positions separated by that enormous orbital diameter. It's like having eyes separated by 300 million kilometers rather than just 6 centimeters. Even the nearest stars, they reasoned, should exhibit a tiny shift against the more distant background stars. This shift is called stellar parallax. Measure this shift, apply basic trigonometry, and the star's distance is revealed. The concept was elegantly simple. Draw a triangle with Earth's orbit as the base and the star as the vertex. Measure the angle at the star and you calculate its distance. Simple geometry that any student learns in school. The execution, however, proved maddeningly difficult, bordering on the impossible. The parallax shift was incredibly tiny, an angle smaller than 1 arcsecond. To grasp this scale, imagine dividing a single degree into 60 parts, each as an arcminute. Divide an arcminute into 60 more parts. Each of those is 1 arcsecond. So 1 arcsecond is a staggering 3600th of a degree. To give you a physical sense of this, if you hold a tennis ball 1 kilometer away, it appears about 1 arcsecond wide. A person standing on a ship's deck 10 kilometers away appears about 1 arcsecond tall. That's the precision 17th century telescopes needed, and they simply couldn't deliver it. The best instruments of the era suffered from mechanical wobbles larger than the signal astronomers sought. Atmospheric turbulence blurred images by several arcseconds, turning pinpoint stars into fuzzy disks. Temperature changes caused telescope parts to expand and contract, throwing off alignment. Even the astronomer's own heartbeat could introduce vibrations large enough to ruin measurements. Observatory foundations settled and shifted. Wind pushed on telescope tubes. It was a battle against every conceivable source of error. Robert Hooke, a brilliant English scientist known for his contributions to optics, mechanics, astronomy and biology, he coined the word cell and formulated Hooke's law of elasticity, attempted the measurement in 1669. He built a specialized telescope mounted high in a tall building, hoping to minimize atmospheric distortion. He observed the bright star Gamma Draconis for months, meticulously recording measurements, and believed he detected a shift. He published his findings, claiming to have measured stellar parallax at last. He was wrong. What Hooke had actually detected was stellar aberration, an entirely different effect caused by the combination of light's finite speed and Earth's motion through space. Light travels at a finite speed, roughly 300,000 kilometers per second, while Earth orbits the Sun at about 30 kilometers per second. When aiming a telescope at a star, you must tilt it slightly in the direction of Earth's motion to compensate for the light travelling down the tube as Earth moves sideways. It's like running through rain. Even if the rain falls straight down, you tilt your umbrella forward because you're moving horizontally. This aberration effect is real and measurable, but it's not parallax. Parallax causes nearby stars to shift against distant background stars. Aberration in contrast makes all stars shift in the same direction by the same amount. Hooke had discovered something profoundly important, just not what he thought. The actual credit for discovering aberration goes to James Bradley in 1728, who correctly deciphered its cause. William Herschel, the discoverer of Uranus in 1781, tried a different ingenious approach. He reasoned that if he observed double stars, pairs of stars appearing close together in the sky, one might be much nearer to Earth than its companion. If so, the closer star should show parallax, while the more distant one served as a fixed reference. Over many years, Herschel made thousands of painstaking measurements of double star systems, meticulously tracking the angular separation between their components. He never found parallax, yet his work was far from wasted. He discovered that many double stars were not just chance alignments of unrelated objects along the same line of sight. Instead, they were physically bound by gravity orbiting each other. He had discovered binary star systems, a monumental finding that transformed stellar astronomy. Binary stars became crucial tools for measuring stellar masses. By observing their orbital periods and separations, astronomers could apply Newton's laws to calculate their individual masses. This technique remains fundamental to astrophysics today. Herschel's failed attempt to find parallax led to an unexpected discovery that unlocked a deeper understanding of stars themselves. A classic example of scientific serendipity guiding us to unforeseen insights. By the early 1800s, measuring stellar parallax had become astronomy's ultimate challenge, its holy grail. Everyone knew it was theoretically possible, but no one could actually achieve it. Dozens of skilled astronomers across Europe dedicated years to the problem, some even claiming success only for their measurements to be irreproducible or wildly inconsistent. The distances were too immense, the angles too minute for the instruments and techniques of the time. Enter Friedrich Wilhelm Bessel, born in 1784 in Minden, Germany. Remarkably, Bessel didn't start his career as an astronomer. He began as an accountant for a trading company, a profession demanding precision and meticulous record-keeping. But in his spare time, he devoured mathematics and astronomy, particularly interested in celestial navigation. At age 20, purely as a hobby, he calculated the orbit of Halley's Comet using old observations. His work was so exceptional that professional astronomer Hinrich Olbers took notice, helping Bessel secure an assistant position at a small observatory. By age 26, Bessel was appointed director of a new observatory in Königsberg, which under his leadership became one of Europe's leading astronomical centres. Bessel transformed into one of the most meticulous scientists of his generation, obsessed with precision and the rigorous analysis of error. This was a radical departure in an era when many scientists made measurements somewhat casually, recording instrument readings without systematically accounting for every potential source of inaccuracy. Bessel was different. He didn't just take measurements. He interrogated every possible source of error, constructed mathematical models to account for them, and repeated observations until he was absolutely certain of his results. He studied how atmospheric refraction, the bending of starlight as it passes through Earth's atmosphere, changed with temperature, humidity, and pressure, developing complex correction formulas. He measured how his telescope's metal parts expanded and contracted with even minute temperature fluctuations. A brass tube could expand by a millimetre or more with a 10 degrees Celsius change seemingly small, but enough to sabotage the precise angular measurements needed for parallax. Bessel attached thermometers to his telescope, measuring its length at various temperatures to derive correction factors. He tracked the mechanical play in his mount, the subtle wobbles in his building's foundation, even the effect of wind pressure on the observatory dome. Every potential source of error was meticulously studied, quantified, and factored into his calculations. This unprecedented level of care, bordering on obsession, was precisely what was needed to finally detect the elusive parallax signal. In 1837, Bessel decided to tackle the parallax problem head-on. He chose his target with strategic brilliance, a star called 61 Cygni, nestled in the constellation Cygnus the Swan. It wasn't a particularly bright star, barely visible to the naked eye under dark skies, what astronomers call a fifth magnitude star. But 61 Cygni possessed one crucial property that strongly suggested it might be relatively close, it moved across the sky faster than almost any other known star. This motion, called proper motion, is the star's actual movement through space over time, distinct from parallax. Most stars appear fixed even over human lifetimes, but a few nearby stars exhibit measurable proper motion. Bessel reasoned quite correctly that a star with high proper motion was likely relatively nearby. Imagine watching cars on a highway from an overpass. The cars in the near lanes seem to zoom past, while distant cars barely appear to move. The same principle applies in space. Nearby stars moving at typical stellar velocities show larger proper motions than distant stars moving at the same speed. 61 Cygni had one of the largest proper motions known, marking it as a prime candidate for parallax measurement. From August 1837 through August 1838, Bessel embarked on a relentless 13-month campaign, making hundreds of observations using a specialised instrument called a heliometer. A heliometer is essentially a telescope with a split objective lens. The front lens is cut in half, and one half can be slid sideways relative to the other. This creates two images of whatever you're observing. By precisely adjusting how much you slide the lens, you can superimpose the two images or separate them by exact amounts, allowing for incredibly precise angular measurements. Bessel's heliometer could measure angles down to about 1/10 of an arc-second, under ideal conditions a monumental feat of engineering and precision for 1837. But Bessel didn't simply point his telescope at 61 Cygni and measure its position in isolation. That would be meaningless without a stable reference frame. Instead, he observed multiple faint reference stars in the same field of view, chosen for their extreme distance, effectively acting as fixed points on the infinite celestial sphere. Every clear night, weather permitting, Bessel measured the angular separation between 61 Cygni and these distant reference stars. He made multiple measurements using multiple references, all to maximize accuracy and ferret out any systematic errors. Over the course of months, as Earth journeyed around its orbit, 61 Cygni traced out a tiny imperceptible ellipse against the background of those reference stars. In January, Earth was on one side of its orbit, and 61 Cygni appeared subtly shifted in one direction. In April, Earth had moved a quarter of the way around, and the shift was different. By July, Earth was on the opposite side, and the shift reversed. By October, the cycle continued. The size of that ellipse directly revealed the star's parallax, but extracting that tiny signal required battling a host of complicating factors, each far larger than the effect Bessel was trying to measure. Atmospheric refraction, for instance, could displace a star near the horizon by half an arc-minute or more, 30 arc-seconds, roughly 100 times larger than the parallax he was seeking. He meticulously measured or calculated these effects and painstakingly subtracted them out. The telescope's metal parts expanded and contracted. The mount had tiny amounts of mechanical play. Earth's axis precessed, causing stellar positions to drift slowly. And then there was aberration, the effect Hooke had mistakenly identified as parallax a century and a half earlier, which made stars appear shifted by about 20 arc-seconds, again far larger than the parallax signal. Bessel had to calculate and remove the aberration effect from every single measurement. He observed at different times of night, recorded air temperature, barometric pressure, and even wind conditions. He attached thermometers to his telescope, developing mathematical formulas relating temperature to instrument length. He built models of mechanical flexure. Every single source of error received its own rigorous mathematical treatment. Only after accounting for everything else, after months of painstaking analysis, could he isolate the tiny parallax signal buried deep within the noise. His monumental result, a parallax of 0.3136 arc-seconds. To truly appreciate this achievement, imagine looking at a dime held at arm's length about 60 centimeters away. The width of that dime as seen from your eye is an angle roughly 20,000 times larger than the parallax Bessel measured. He was measuring an angle approximately equal to the width of a human hair seen from 100 meters away, or the angle subtended by the period at the end of this sentence seen from across a football field. From this measurement using basic trigonometry, Bessel calculated that 61 Cygni was about 10.3 light-years away, roughly 97 trillion kilometres. To put this in staggering perspective, if you could somehow drive to 61 Cygni at highway speed, say 100 kilometers per hour, the trip would take about 110 million years. Modern measurements utilizing far superior instruments place 61 Cygni at 11.4 light-years. Bessel's result, accurate to within about 10% for 1838, was an astonishing triumph of human perseverance and intellect. This was extraordinary work. 13 months of nearly continuous observations, hundreds of individual measurements, followed by months of mathematical analysis and error calculation, all done by hand using logarithm tables since electronic calculators were a century in the future. It's precisely why no one had succeeded before. The required precision pushed the absolute limits of 1838 technology, yet Bessel achieved it through obsessive attention to detail profound mathematical skill and relentless patience. Within months of Bessel's announcement in late 1838, the floodgates of discovery burst open. Thomas Henderson, a Scottish astronomer working at the Royal Observatory in Cape Town, South Africa, published his own parallax measurements for Alpha Centauri. Intriguingly, Henderson had actually made his observations before Bessel, starting back in 1832. He had carefully measured Alpha Centauri's position over many months, seen a shift that looked like parallax but was perhaps too cautious. He worried about systematic errors, questioned his instrument's accuracy, and so hesitated to publish. When Bessel's announcement came in early 1839, Henderson realised his own measurements were valid and rushed to publish. His data in some ways was even better than Bessel's, because Alpha Centauri is brighter and closer, making its parallax larger and easier to measure. Alpha Centauri, it turned out, was even closer than 61 Cygni at about 4.4 light-years. This highlights a fascinating aspect of the history of science. Henderson made the first stellar parallax measurements, but Bessel gets credit for the discovery because he published first. It underscores the competitive yet collaborative nature of scientific progress, where priority in publication is key. Soon after, Friedrich Georg Wilhelm von Struve, working at the Dorpat Observatory in what is now Tartu, Estonia, measured Vega's parallax. Struve was another meticulous observer who had been tackling the parallax problem for years. Vega, being much farther than the other two stars at about 25 light-years, presented an even tinier and more challenging parallax to measure. While Struve's measurement was less accurate than Bessel's or Henderson's, it was a genuine detection. Suddenly, after 2 millennia of profound mystery regarding stellar distances, humanity possessed the distances to 3 stars with many more on the horizon. Astronomers worldwide initiated parallax programs, and within a few years distances to dozens of stars were measured. By the early 1900s, hundreds of stars had measured parallaxes, and by the mid-20th century, thousands. Each measurement unequivocally confirmed that stars were scattered at enormous distances, far beyond anything in our solar system. The nearest star, Alpha Centauri, was 40 trillion kilometers away, about 270,000 times farther than the Sun. Sirius, one of the brightest stars in our sky, was 81 trillion kilometers away. More distant stars were even farther. This cascade of discoveries fundamentally reshaped humanity's understanding of the universe's scale. Before parallax measurements, some astronomers conjectured the Milky Way might be only a few thousand astronomical units, across perhaps 100 times the size of the solar system. After Bessel's work, it became blindingly clear the galaxy was millions of times larger. Our Sun wasn't at the centre of a small contained stellar system. It was one ordinary star among countless others scattered across distances so vast they were almost impossible to comprehend. Our sense of cosmic scale expanded enormously. The universe transformed from a relatively small solar system, surrounded by a sphere of nearby stars, into an unimaginably vast cosmos, brimming with objects at distances requiring trillions of kilometers to describe. This revelation was as revolutionary as Copernicus's discovery that Earth orbited the Sun, or Galileo's telescopic unveiling of Jupiter's moons. As these staggering measurements accumulated, astronomers faced a practical problem. How do you effectively communicate and work with such enormous numbers? Writing out 97 trillion kilometres repeatedly became tedious and cumbersome. Scientific papers were filled with unwieldy figures. Expressing a star's distance as 657,000 on astronomical units was awkward. Using multiples of the sun's distance helped somewhat, but it still wasn't ideal. Someone, though history isn't entirely clear on who first proposed it, suggested defining a new unit based directly on the elegant geometry of parallax. The idea was beautifully simple and flowed naturally from the measurement technique itself. Imagine a right triangle. One side, the base, is defined as 1 astronomical unit AU, the average distance from Earth to the Sun. The angle opposite that base at the vertex where the star sits is defined as 1 arc-second. Now solve for the length of the long side of this triangle, the hypotenuse, which represents the distance to the star. Using basic trigonometry, specifically the tangent function, this distance works out to approximately 265 astronomical units. In more familiar terms, that's about 30.9 trillion kilometres, or roughly 19.2 trillion miles. They called this distance the parsec, a clever contraction of parallax and arc-second. The name itself immediately tells you exactly how it's defined. Here's the crucial insight: 1 arc-second was chosen because it's a round number within the angular measurement system humanity invented millennia ago. The Babylonians around 2000 BCE developed a base 60 number system. They divided circles into 360 degrees because 360 has many factors, making it easy to divide into halves, thirds, quarters, and so on. They further divided degrees into 60 arc minutes, and arc minutes into 60 arc seconds for the same reason. This sexagesimal system, based on the number 60, is why we still measure time in 60 minutes and 60-second hours. The Babylonians invented it, the Greeks adopted it, and it spread throughout the ancient world, persisting to this day. But there is nothing physically special about this choice. It's pure mathematical convenience rooted in ancient numbering preferences. An alien civilization using a different angular system might define their angular units differently. The parsec is therefore a consequence of human choices about how to measure angles, not anything fundamental or inherent to the universe itself. And here's another paradox: virtually no star actually sits at exactly 1 parsec from Earth. Our nearest stellar neighbour, Proxima Centauri, is about 1.302 parsecs away, according to the latest Gaia satellite measurements, the most accurate distance we have. The brilliant star Sirius, prominent in winter skies, is approximately 2.64 parsecs. Vega, one of the brightest stars in summer skies, is about 7.7 parsecs. Even Bessel's pioneering star 61 Cygni is approximately 1.03 parsecs. The parsec doesn't mark any natural cosmic boundary. It's not a distance where any particular physical process occurs, nor do stars suddenly behave differently at 1 parsec. There's no sphere of special significance at that distance. It's simply the distance that makes parallax arithmetic incredibly convenient, defined by an arbitrary yet deeply embedded angular choice. But that convenience for working astronomers proved to be absolutely enormous. For astronomers performing parallax measurements daily, the parsec offered one monumental advantage over any other distance unit. If you measure a star's parallax in arc-seconds, its distance in parsecs is simply 1 divided by that number. The relationship is direct and transparent. If a star shows a parallax of 0.5 arc-seconds, it's 2 parsecs away. If it's 0.25 arc-seconds, it's 4 parsecs. 0.1 arc-seconds makes it 10 parsecs. 0.05 arc-seconds, 20 parsecs. This allows for mental arithmetic, no calculator needed, no complex conversions, no looking up tables, just invert the parallax and you have the distance. When processing hundreds or thousands of measurements by hand, as astronomers did for decades before computers, this directness was invaluable. Imagine working through a notebook full of parallax measurements, star A 0.15 arc-seconds, that's 6.67 parsecs, star B 0.28 arc-seconds, that's 3.57 parsecs, star C 0.08 arcseconds. That's 12.5 parsecs. You could perform this math in your head, maintaining a fluid workflow. This transparent relationship even served as a quick error check. If you accidentally measured 0.5 arc seconds instead of 0.05, the distance would come out to 2 parsecs, and you'd immediately know something was wrong because that would make the star one of the very nearest in the sky, a fact that would be obvious from its brightness and other properties. Using kilometers or miles would require multiplying by massive conversion factors every single time, inviting arithmetic errors. Using astronomical units would demand dividing by 206 to 65 repeatedly. Even light years would necessitate multiplying by about 3.26 every time. Each calculation became an opportunity for mistakes. The Parsec eliminated that. By the late 1800s, with dozens of reliable parallax measurements confirming the enormous scattered distances of stars, the Parsec became the natural, unassailable unit for expressing those distances. This wasn't an official decree by a committee. It happened organically because it was genuinely useful. Astronomers began using it in their papers because it streamlined their work. Other astronomers reading those papers adopted it because it made the results easier to interpret. Catalogues started listing distances in parsecs, and textbooks explained the concept. By 1900, it had become the default unit for stellar distances in professional astronomy. As telescope technology improved and observations reached ever deeper into the cosmic abyss, astronomers soon needed larger multiples of the parsec. By the early 1900s, they were measuring distances to star clusters hundreds or thousands of parsecs away. Repeatedly writing out 3,000 parsecs became cumbersome, so borrowing from the metric system's prefixes, they invented the kiloparsec, meaning 1,000 parsecs. A typical globular cluster, a spherical collection of hundreds of thousands of ancient stars, might be 15 kiloparsecs away. The very centre of our Milky Way galaxy is about 8.2 kiloparsecs from Earth. Then, in the 1920s, Edwin Hubble made one of astronomy's most profound discoveries. Those fuzzy spiral nebulae which astronomers had been cataloguing for decades were not mere gas clouds within our galaxy. They were separate galaxies, island universes, containing billions of stars located at truly staggering distances. Hubble's breakthrough came from observing Cepheid variable stars in the Andromeda Nebula. Using the 100-inch telescope on Mount Wilson, then the largest telescope in the world, he could resolve individual stars in Andromeda. Some of these were Cepheid variables which pulsate with regular predictable periods. Henrietta Leavitt's period luminosity relationship, discovered in 1912, had revealed that Cepheids with longer pulsation periods are intrinsically brighter. Hubble measured the periods of Cepheids in Andromeda, determined their true luminosities, compared them to how bright they appeared from Earth, and calculated the distance. The answer initially was about 280 kiloparsecs. Modern measurements refined over decades place Andromeda at 780 kiloparsecs. So while Hubble's initial distance was too small by a factor of nearly 3, it was still unequivocally far beyond the Milky Way's boundaries. The Andromeda Galaxy, our nearest large spiral neighbour, is about 780 kiloparsecs away, 780,000 parsecs. Writing that number repeatedly was again tedious, so astronomers invented the megaparsec, meaning 1 million parsecs. Andromeda is 0.78 megaparsecs away. Other galaxies proved even farther. The Virgo cluster of galaxies is about 16 megaparsecs away, and the Coma cluster is about 100 megaparsecs. These immense distances measured in megaparsecs provided the crucial evidence for the expansion of the universe, which Hubble discovered in 1929, revolutionizing our cosmic understanding. As observations pushed even deeper into the cosmos, revealing the large-scale structure of the universe itself, the gigaparsec emerged 1 billion parsecs. Distant galaxy clusters now sit at distances measured in hundreds or thousands of megaparsecs. The edge of the observable universe, the farthest distance from which light has had time to reach us since the Big Bang, is about 14 gigaparsecs in moving coordinates. We had taken a unit originally based on a convenient angular measurement for nearby stars and kept multiplying it by thousands, millions and billions, simply because the universe kept getting bigger in our observations. At each stage, the parsec stuck around. Why? Because converting everything to a new unit would have been far more work than simply adding a prefix. The entire astronomical infrastructure, all the formulas, all the catalogues, all the mental habits of astronomers was already built around parsecs. Switching would have required a massive coordinated effort across the entire field for unclear incremental benefit. To truly understand why the parsec became absolutely foundational to modern astronomy, we need to appreciate the transformation of the early 20th century. This was when astronomy shifted from a science of individual observations by single astronomers to a science of massive systematic surveys producing unprecedented data sets. The Harvard College Observatory, under the visionary direction of Edward Pickering starting in 1877, embarked on an ambitious project to photograph the entire sky, visible from both their Massachusetts location and from a new observatory they established in Arequipa, Peru, to cover the southern hemisphere. Over several decades working with relatively primitive photographic plates, they amassed over 500,000 photographs each, capturing thousands of stars. This was an unprecedented deluge of data, far more information than any previous astronomical project had generated. Pickering needed an army of dedicated individuals to analyse it all, to examine each plate measure, star positions and brightnesses, and meticulously classify stellar spectra. This was tedious, time-consuming work, demanding keen eyesight, unwavering attention to detail and considerable mathematical skill. Pickering hired a team of women for this monumental task, often referred to as computers, because their primary job was to compute stellar properties from the photographic plates. These women, despite being paid significantly less than male astronomers and frequently receiving no formal credit for their groundbreaking work, made some of astronomy's most important discoveries. Annie Jump Cannon classified over 350,000 stellar spectra, developing the stellar classification system still used today. At her peak, she could classify 3 stars per minute, making her the most prolific classifier in history. Williamina Fleming discovered over 300 variable stars and 10 novae. Cecilia Payne-Gaposchkin, building on this work, would later demonstrate that stars are primarily made of hydrogen and helium, not the heavier elements found on Earth. But for our story, the most important of the Harvard computers was Henrietta Swan Leavitt. Leavitt was meticulously analysing variable stars in the Magellanic Clouds, 2 small satellite galaxies visible from the southern hemisphere. Variable stars are, as the name suggests, stars whose brightness changes over time. Some vary randomly, flaring and dimming unpredictably, but others pulsate with remarkably regular periods, getting brighter and dimmer in a repeating cycle. Leavitt focused on a specific type called Cepheid variables, named after the star delta Cepheid, which pulsates with a period of about 5 days. In 1912, after years of patient painstaking work, measuring Cepheid periods and brightnesses, Leavitt made a revolutionary discovery. She found that Cepheid variables' pulsation periods directly relate to their intrinsic luminosity. Simply put, longer period Cepheids are genuinely brighter stars. A Cepheid that pulsates with a 30-day period is intrinsically more luminous than one with a 10-day period, which in turn is brighter than one with a 3-day period. This relationship was tight, predictable, and quantifiable. This discovery changed everything for distance measurements. If you observe a Cepheid variable anywhere in the universe, measure its pulsation period, you immediately know its true intrinsic brightness. Compare that to how bright it appears from Earth, and you can calculate how far away it is using the inverse square law. Light spreads out as it travels, so brightness falls off as the square of distance. If something appears 4 times dimmer than expected, it must be twice as far away. It's like knowing a light bulb is 100 watts. You can judge its distance by how dim it appears. A 100-watt bulb seen from 10 meters away appears much brighter than the same bulb seen from 100 meters away. Cepheids became astronomy's standard candles objects whose true brightness is known, allowing astronomers to measure distance by comparing true to apparent brightness. The crucial detail is that Cepheids are genuinely luminous stars. A typical Cepheid shines with the light of thousands of suns. They are bright enough to be seen in other galaxies, even millions of parsecs away. This allowed astronomers to measure distances far beyond the reach of parallax. With early 20th century technology, parallax was reliable only out to a few hundred parsecs for the brightest stars. Ground-based telescopes peering through Earth's turbulent atmosphere simply couldn't measure the tiny angles needed for more distant objects. Cepheids extended distance measurements to millions of parsecs, thousands of times farther than parallax alone could reach. But here's the key point for understanding the parsec's enduring dominance. To calibrate the Cepheid period luminosity relationship, you first need to know the actual distances to some nearby Cepheids. You need to establish exactly how much brighter a 30-day Cepheid is than a 10-day Cepheid. And the only way to measure those fundamental distances was through parallax for the nearest Cepheids, or statistical parallax methods that average over many stars. The entire cosmic distance ladder, the suite of techniques that allows us to measure distances to the farthest galaxies and determine the universe's scale, all of it traces back to those original parallax measurements. Parallax gives distances to nearby stars in parsecs. Those parsec distances calibrate the Cepheid relationship. Cepheids in turn give distances to galaxies in megaparsecs, and those megaparsec distances to galaxies then calibrate type Ia supernovae, which extend to gigaparsecs. Every step builds upon the previous one, and every measurement naturally comes out in parsecs, because that's what parallax, the bedrock, inherently produces. So the parsec didn't just become standard for nearby stars, it became the fundamental cornerstone for all astronomical distance measurements. Every subsequent technique, every new rung on the distance ladder was calibrated using parsec distances. The unit propagated throughout astronomy not merely because it was convenient for parallax work, but because parallax was the immutable bedrock upon which everything else stood. While professional astronomers universally embraced the parsec across all sub-disciplines, popular science, driven by a different imperative, went a completely different direction. The space race of the 1950s and 60s ignited massive public interest in astronomy and space exploration. Sputnik in 1957, Gagarin in 1961, Apollo 11 in 1969, these events captivated millions. Suddenly a vast public audience craved knowledge about the cosmos. Popular books, magazine articles, television shows and planetariums all needed to communicate astronomical distances to general audiences. And almost universally they used light years instead of parsecs. Carl Sagan's iconic Cosmos television series, which aired in 1980 and captivated over 600 million people worldwide, used light years exclusively. When Sagan spoke of Alpha Centauri, he said it was 4.24 light-years away. When he discussed the Milky Way's size, he reported it as 100,000 light-years in diameter. Distant galaxies were always presented in millions or billions of light-years. Not once in 13 episodes did he utter the word parsec. This made perfect sense for public communication. The concept of a light-year explains itself. Light is universally understood as the fastest thing in the universe, and a year is a time span everyone intuitively understands. Therefore, a light year is self-evidently a colossal distance, the distance light travels in 1 year at its incredible speed. The name itself conveys the concept. It's intuitive, evocative, and requires no specialized explanation. The parsec, in stark contrast, demands extensive explanation. You must first explain what parallax is, why we use it, what an arcsecond is, and where that angular unit originates. You have to diagram the geometry and explain why astronomers chose that particular seemingly arbitrary angle. Even after all that most people still find it abstract and unintuitive, it doesn't connect to everyday experience the way a light year does. The light year also carries a poetic resonance. When you state that Andromeda is 2.5 million light-years away, people immediately grasp that we are seeing light that left Andromeda 2.5 million years ago. We are literally looking back in time. The photons striking our telescopes began their journey when our distant ancestors were just learning to fashion crude stone tools. That's evocative, profound, and deeply meaningful. Saying Andromeda is 0.78 megaparsecs away, while accurate to a professional, simply doesn't have the same emotional impact. It doesn't immediately connect to anything in human experience. Thus, a persistent split emerged that endures to this day. Professional astronomers use parsecs in their research. Every peer-reviewed paper, every technical catalogue, every scientific discussion uses parsecs, kiloparsecs, or megaparsecs. But popular science consistently uses light years. Every news article, every documentary, every museum exhibit explains distances in light years. It's the same astronomer describing the same galaxy, but using a different number depending on the audience. An astronomer writing a paper for the Astrophysical Journal will report a galaxy as 300 megaparsecs away. That same astronomer interviewed for a New York Times article about the identical galaxy will say it's about 9 to 80 million light-years away. They are describing the same distance, just expressed in different units for different audiences. This dual system, while pragmatic, does create some confusion. People steeped in popular astronomy books think in light-years. Then, if they pursue an astronomy course or attempt to read research papers, suddenly everything is in parsecs. They must learn the conversion factor, 3.226 light-years per parsec, and mentally convert while reading, which acts as a minor but persistent barrier to engagement with professional astronomy. However, both communities maintain legitimate reasons for their choices. Professional astronomers continue to use parsecs because it connects directly to their fundamental measurement techniques, and their entire scientific infrastructure is built upon parsec units. All their databases store distances in parsecs, all their software expects parsec inputs, and all their formulas are written with parsecs. Switching would necessitate changing millions of lines of code, reformatting countless databases and rewriting textbooks, a monumental, costly and disruptive undertaking. Popular science conversely continues to use light years because audiences find them more understandable, and the name itself is evocative and memorable. Science communicators aim to ignite imagination. Saying a star is 4 light-years away makes people ponder light travelling for 4 years. It's interesting and thought-provoking. Saying the same star is 1.3 parsecs away sounds purely technical and dry. The parsec's dominance in professional astronomy was reinforced and expanded enormously by space missions of the late 20th and early 21st centuries. In 2013, the European Space Agency launched a satellite called Gaia, with an extraordinarily ambitious goal to measure precise positions and distances for over 1 billion stars, roughly 1% of all the stars in our Milky Way galaxy. Gaia carries 2 telescopes that continuously scan the sky. As the satellite slowly rotates, each star passes through its field of view multiple times over the mission's lifetime. The satellite measures each star's position with incredible precision, down to micro-arc seconds for the brightest stars. That's 1/1,000,000th of an arc second. To put this in perspective, this is equivalent to measuring the width of a human hair from 1,000 kilometers away, or measuring the size of a coin on the moon as seen from Earth. This level of precision allows Gaia to detect parallax for stars much, much farther away than ever before. Previous catalogues from ground-based observations reliably reached maybe a few hundred parsecs. Gaia extended reliable parallax measurements to several kiloparsecs for bright stars. By 2022, Gaia had released data on over 1.8 billion stars, creating the most comprehensive and precise 3-dimensional map of our galactic neighbourhood ever created. This dataset includes distances, 3-dimensional positions, proper motions showing how stars move through space, brightness in multiple wavelength bands, colours and spectroscopic data for many stars. This treasure trove of data has transformed essentially every branch of astronomy. Studies of stellar evolution now use Gaia distances to create exquisitely precise Hertzsprung-Russell diagrams. Studies of the Milky Way structure use Gaia data to map spiral arms and measure the galaxy's rotation. Studies of star formation use Gaia to identify young stellar clusters and trace how stars emerge from molecular clouds. Exoplanet studies use Gaia parallaxes to determine precise planet radii and densities. Almost every astronomical paper published since 2022 cites Gaia data somewhere, and every single distance in the Gaia catalogue is reported in parsecs. This wasn't just traditional convention, it was the natural logical choice because Gaia, fundamentally measures parallax. This satellite's primary output is parallax measurements in arcseconds. Each star has a measured parallax and uncertainty in that parallax, and flags indicating the reliability of the measurement. Converting those parallaxes to distances in parsecs is trivial, simply one divided by the parallax in arcseconds. Converting to any other unit requires additional steps and additional opportunities for errors. More importantly, Gaia was a multi-billion-dollar mission developed over 2 decades by hundreds of scientists and engineers across Europe. The entire data processing pipeline, all the software that reduces raw satellite measurements to final catalogue values, all the analysis tools that astronomers use to work with the data, everything was built around parsecs from its inception. This single mission has probably ensured the parsec's dominance for at least another 50 years. Too much infrastructure now depends on it. Too many people have learned to think in parsecs. Too many tools assume parsec inputs. Switching would require a massive coordinated effort across the global astronomy community, a monumental undertaking that no one currently has the incentive or power to enforce. Gaia's extreme precision also revealed something interesting about the parsec definition itself. The simple geometric definition that Bessel would recognise has evolved considerably. Modern parallax measurements must account for Earth's orbit not being perfectly circular, but slightly elliptical. They account for gravitational tugs from other planets, particularly Jupiter and Saturn, that subtly shift Earth's position. They account for the Moon, which causes Earth to wobble slightly as the Earth-Moon system orbits their common centre of mass. They even account for light bending due to the Sun's gravity, an effect Einstein predicted in his general theory of relativity. Starlight passing very close to the Sun's edge gets deflected by about 1.75 arc-seconds. That's larger than the parallaxes Gaia measures, so it must be meticulously corrected for. This relativistic deflection varies with how close the star appears to the Sun and changes throughout the year as Earth orbits. So the simple straight-line geometry implied by the original parsec definition is actually an approximation. The modern parsec is defined more carefully, accounting for these subtle yet crucial relativistic effects. The International Astronomical Union formally updated the parsec definition in 2015 to include these corrections, but the basic concept remains the same. 1 parsec is still fundamentally the distance at which 1 astronomical unit subtends 1 arc-second, just with all the subtle corrections that modern precision requires. 1 parsec equals 3.266 and 1/16 light years. You can remember this as roughly 3¼ light years. If you don't need absolute precision, light leaving a star 1 parsec away takes about 3 years and 3 months to reach Earth. In more everyday units, a parsec is about 30.9 trillion kilometres or 19.2 trillion miles. These numbers are genuinely difficult for human brains to comprehend. Our cognitive systems evolved to understand distances we can walk or throw rocks across, not distances requiring trillions of kilometres to describe. To make this more concrete, consider the Parker Solar Probe, NASA's audacious mission to study the Sun's corona by flying closer to the Sun than any previous spacecraft. Launched in 2018, it uses multiple Venus flybys to gradually drop deeper into the Sun's gravity well. At its maximum speed during close approaches to the Sun, the Parker Solar Probe reaches about 192 kilometers per second, 119 miles per second. It is the fastest human-made object ever built, moving at about 0.06% of light speed. At this incredible velocity, crossing just 1 astronomical unit from Earth to the Sun takes about 9 days. Voyager 1 launched in 1977, and now in interstellar space took 35 years to travel 40 trillion kilometers from the Sun, which is only about 1.3 parsecs. At the Parker Solar Probe's peak speed, if it were heading to a star 1 parsec away instead of orbiting the Sun, the journey would take about 500 years. Proxima Centauri, our nearest stellar neighbour at 302 parsecs would take the Parker Solar Probe roughly 6,600 years to reach. Sirius at 2.64 parsecs would take about 13,500 years. Even Alpha Centauri A and B, which are closer than Sirius, would take over 6,000 years. These are not abstract numbers. They are the brutal reality of cosmic distances versus our current technology. Even our fastest spacecraft, pushing the boundaries of what chemical rockets and gravity assist can achieve, would require thousands of years to reach even the nearest stars. This is precisely why interstellar travel remains firmly in the realm of science fiction for now. The distances are simply too vast for any propulsion system we can currently build. Chemically propelled rockets are limited by the energy density of chemical bonds. Nuclear rockets could do better, perhaps reaching a few % of light speed, reducing the trip to Proxima Centauri to perhaps 100 years instead of thousands. Theoretical concepts like nuclear pulse propulsion, detonating nuclear weapons behind a spacecraft and riding the shockwave might reach 10% of light speed. Laser-pushed light sails using powerful ground-based lasers to accelerate tiny probes might reach 20% of light speed. But all of these are theoretical. No one has actually built them, and even at 20% of light speed, Proxima Centauri is still over 20 years away. Unless we develop fundamentally new physics, perhaps something like an Alcubierre warp drive that somehow circumvents relativity's cosmic speed limit, practical interstellar travel with human crews remains far beyond our capabilities. We can barely get to Mars, and that's only 0.3 parsecs away. Let me now explain why the parsec matters so much for actual astronomical research, beyond just being a convenient unit for simple, parallax calculations. One of the most important analytical tools in stellar astrophysics is the Hertzsprung-Russell diagram, often called the HR diagram. This is a plot that charts stars' temperatures, usually expressed as spectral type, or colour, on one axis, and their luminosities, their true intrinsic power output, on the other. When you plot thousands of stars on this diagram, clear, profound patterns emerge. Most stars fall along a diagonal band running from hot, bright stars in the upper left to cool, dim stars in the lower right. This is called the main sequence, and it represents stars actively fusing hydrogen into helium in their cores, like our own Sun. Giants cluster in a region toward the upper right. These are evolved stars that have exhausted their core hydrogen and expanded to enormous sizes. White dwarfs cluster in the lower left, hot but dim because they are so incredibly small. These patterns, akin to a stellar Rosetta Stone, reveal how stars evolve over their lifetimes. A star like the Sun begins on the main sequence, gradually brightens. As it ages, eventually exhausts its core hydrogen and swells into a red giant, then sheds its outer layers to become a white dwarf. Massive stars follow even more dramatic paths, becoming supergiants and ultimately exploding as supernovae. But to create an accurate Hertzsprung-Russell diagram, you need to know a star's true luminosities, its actual power output. What you observe from Earth is apparent brightness, how bright the star looks to you. But apparent brightness depends on both the star's true luminosity and its distance. A dim star nearby can appear just as bright as a luminous star far away, much like a candle held close to your eye can appear as bright as a distant searchlight. To convert apparent brightness to true luminosity, you absolutely unequivocally need its distance. And here's where the parsec shows its profound utility in a way that other units simply don't. Astronomers define something called absolute magnitude as how bright a star would appear if it were placed at exactly 10 parsecs distance. This standardizes all comparisons. Every star's absolute magnitude tells you its true luminosity on an equal footing, as if all stars were lined up at the same fixed distance. The conversion formula is elegantly simple when using parsecs. Absolute magnitude, apparent magnitude, 5 log 10, distance in parsecs, plus us does 5. That plus us at the end comes directly from the reference distance being 10 parsecs. If you try to use any other distance unit, you have to inject messier conversion factors into the formula, making it longer, more complex, and significantly more prone to arithmetic errors. For example, if you wanted to use light years, the formula becomes absolute magnitude, apparent magnitude, 5 log 10 distance in light years, 32.6, where 32.6 light-years is the equivalent of 10 parsecs. That division by 32.6 is awkward and makes the arithmetic harder. This might seem like a minor detail, but when you're performing thousands or millions of these calculations, as astronomers routinely do with large data sets, keeping everything in one consistent unit prevents countless errors. Switching between units mid-calculation is precisely how mistakes happen. You forget a conversion somewhere, or you apply a conversion factor in the wrong direction, and suddenly your derived luminosities are catastrophically wrong. Modern distance measurement doesn't rely on parallax alone. Instead, astronomers employ multiple independent techniques that cross-check each other, building what's known as the cosmic distance ladder. Each rung of this ladder reaches farther into space, but crucially it relies on calibration from the rungs below it. This redundancy provides crucial validation. If two independent methods yield similar distances to the same object within their uncertainties, we can be confident the answer is correct. The bottom rung, the foundational step, is parallax. This provides direct geometric distances to nearby stars based purely on triangulation. No assumptions about stellar physics are required. No models of how stars shine, just pure geometry. You measure angles, you get distances. Parallax is absolutely reliable within its range, which with Gaia extends to several thousand parsecs for the brightest stars and a few hundred parsecs for typical stars. The second rung uses spectroscopic parallax, which despite the name has nothing to do with actual parallax. It's perhaps one of the worst named techniques in astronomy. Spectroscopic distance estimation would be more accurate. This technique analyzes a star's spectrum in detail to determine its type, and by extension estimate its intrinsic luminosity. Compare the estimated luminosity to its apparent brightness, and you can calculate its distance. This method reliably works out tens of thousands of parsecs. The third rung utilizes Cepheid variables, employing Henrietta Leavitt's groundbreaking period-luminosity relationship. Measure the pulsation period, which can be done photometrically. Without needing spectra, determine the true luminosity from the period, compare it to apparent brightness, and calculate the distance. Cepheids are luminous enough to be seen in other galaxies, with large telescopes extending measurements to millions of parsecs. The fourth and highest rung employs Type Ia supernovae. These are exploding white dwarf stars in binary systems. The white dwarf accretes matter from a companion star until it exceeds a critical mass of about 1.4 solar masses, known as the Chandrasekhar limit. At this precise mass, carbon fusion ignites explosively in the degenerate core and the star detonates. Because all Type Ia supernovae reach roughly the same critical mass before exploding, they also achieve remarkably consistent peak brightnesses. When you observe a Type Ia supernova in a distant galaxy, you know almost precisely how bright it truly was at maximum light. Compare that to how bright it appears, and you can calculate its distance. Type Ia supernovae are extraordinarily luminous at their peak, briefly outshining their entire host galaxy. They can be seen billions of parsecs away, extending measurements across a significant fraction of the observable universe. This is precisely how we measured cosmic acceleration and discovered dark energy in the late 1990s, a discovery that won the 2011 Nobel Prize in Physics. Each technique in this cosmic distance ladder comes with its own set of uncertainties. Parallax measurements have observational errors stemming from photon noise, atmospheric turbulence for ground-based telescopes, and subtle systematic effects. Spectroscopic parallax relies on stellar models that might be imperfect. The Cepheid period-luminosity relationship has some intrinsic scatter, meaning not all Cepheids of the same period have exactly the same luminosity. Type Ia supernovae, while remarkably consistent, aren't perfectly uniform, exhibiting variations of 10% to 20%. These uncertainties compound as you climb higher up the ladder. A 10% error in Cepheid distances propagates into a 10% error in anything calibrated using Cepheids. A 15% error in supernova distances affects cosmological parameters derived from supernova. Managing these error budgets is one of the major challenges in observational cosmology, but by employing multiple independent methods and constantly checking for agreement, astronomers build confidence in their distance measurements. If Cepheids and surface brightness fluctuations both yield the same distance to a galaxy, within uncertainties that's reassuring. If they disagree significantly, something is fundamentally wrong and more investigation is needed. Throughout this entire ladder from the first step to the last parsecs, provide the consistent framework. Every technique outputs distances in parsecs, kiloparsecs or megaparsecs. Every calibration uses parsec distances. The whole intricate system hangs together because everybody is speaking the same unit language. Converting to different units at each step would only introduce additional opportunities for errors and confusion. One of the most important numbers in all of cosmology is the Hubble constant. This quantifies the rate at which the universe is expanding. In the 1920s, Edwin Hubble, using Cepheid variables to measure galaxy distances and spectroscopy to measure their recession velocities, discovered a remarkable relationship. Distant galaxies are receding from us, moving away as space itself expands, and the farther away they are, the faster they recede. The relationship is linear: double the distance, double the recession velocity. The Hubble constant quantifies this relationship. Its value is somewhere around 67 to 74 kilometers per second per megaparsec, depending on which measurement method you trust. What this means is that for every megaparsec of distance, a galaxy's recession velocity increases by that many kilometers per second. A galaxy 1 megaparsec away recedes at about 70 km/s. A galaxy 2 megaparsecs away recedes at about 140 km/s. A galaxy 10 megaparsecs away recedes at about 700 km/s. At large enough distances, these recession velocities, driven by the expansion of space, approach the speed of light. This isn't motion through space, but space itself, expanding between us and the galaxy. Recent measurements from different techniques disagree about the Hubble constant's exact value, and this disagreement is one of the biggest unsolved problems in cosmology, a profound Hubble tension. Observations of the cosmic microwave background. The afterglow of the Big Bang analysed using our best cosmological model with parameters from the Planck satellite yield a value around 67.4 st/s per megaparsec. Measurements using the cosmic distance ladder, starting with parallax to calibrate Cepheids, and using Cepheids to calibrate Type Ia supernovae, give a value around 73 kiloquares per megaparsec. That's about an 8% disagreement. Crucially, the two measurements have uncertainties of only about 2% or 3%, so they disagree at multiple sigma significance, a statistically worrisome discrepancy. This Hubble tension is genuinely worrying. Either one of the measurement techniques has a subtle, unrecognized systematic error, or our standard cosmological model is missing something fundamental. Perhaps dark energy behaves differently than we think, changing its density over time. Perhaps there's some unknown physics affecting cosmic expansion, or neutrinos have slightly more mass than we thought, or there's an undiscovered particle. Resolving this tension is a major goal of observational cosmology, with high stakes for our understanding of the universe. Notice the units of the Hubble constant kilometers per second per megaparsec velocity per distance. The parsec is explicitly baked into the fundamental equation, describing how fast the universe is expanding. You could convert to other units. Some cosmologists use inverse gigayears, which has dimensions of inverse time, making the expansion rate look like a frequency. But most use kilometers per second per megaparsec because that's how we measure it. We measure galaxy recession velocities in kilometers per second from spectroscopic redshifts, and we measure distances in megaparsecs using the distance ladder. So the natural units for the Hubble constant are kilometers per second per megaparsec. Using anything else requires conversions that don't add clarity. One elegant aspect of the parsec is how it seamlessly connects different measurement scales across astronomy. At its foundation is the astronomical unit AU, the average distance from Earth to the Sun. This used to be a measured value determined through various ingenious techniques. In the 18th and 19th centuries, astronomers observed transits of Venus across the Sun's face from different locations on Earth. The parallax of Venus against the Sun, triangulated from Earth, yielded the Earth-Sun distance. In the 20th century, radar ranging became possible. We bounce radio signals off planets like Venus and Mars, measure the round-trip time multiply by the speed of light, and calculate distances with incredible precision. Modern measurements of the astronomical unit are accurate to within meters out of 150 million kilometers. In 2012, the International Astronomical Union (IAU) made a key decision. They redefined the astronomical unit as a fixed constant rather than a measured value. It is now defined as exactly 149,597,870.7 kilometers, not approximately but exactly. This makes the AU a defined unit similar to how the meter is defined in terms of the speed of light travelling a certain distance in a vacuum. The parsec builds directly on the AU through its geometric definition. 1 parsec equals exactly 206,264.806,247 astronomical units. Since the AU is now a defined constant, the parsec is also a defined constant. Its length is exactly 30.85 trillion kilometers, no longer a measured value but a fixed precise definition. The speed of light connects parsecs to light years through another defined constant. The speed of light in vacuum is defined as exactly 290,792,450 meters per second. A light year is exactly how far light travels in 1 Julian year of 365.25 days, which works out to exactly 9.4 trillion kilometers. Using these definitions, 1 parsec equals exactly 3.2615378 light years, good to many decimal places. These interconnections allow for powerful cross-checks. You can measure a distance via parallax-yielding parsecs, convert to light years using the exact conversion factor, independently measure light travel time EBG. If you're observing something with changing brightness or periodicity, the numbers should match within uncertainties. If they don't, something is wrong with one of your measurements, prompting further investigation. This kind of cross-validation is crucial in science. No measurement technique is perfect. All have systematic errors that might go unnoticed. By using multiple independent approaches and checking for consistency, we catch errors and build confidence in our results. For nearby objects within a few hundred parsecs, the simple parsec definition works beautifully. Space is approximately flat on these scales, and light travels in essentially straight lines. The geometric definition applies cleanly. But for objects millions or billions of parsecs away, reality becomes significantly more complicated. Einstein's general theory of relativity, published in 1915-16, showed that mass and energy curve space-time. Light doesn't travel in perfectly straight lines through space. It follows curved paths called geodesics, guided by the geometry of space-time itself. Massive objects like galaxies and galaxy clusters create significant space-time curvature, bending the path of light passing nearby. Gravitational lensing provides dramatic evidence of this. Light from a distant quasar, a luminous active galactic nucleus, passing very close to a massive galaxy, along our line of sight, gets bent and deflected. Sometimes the bending is so strong that we see multiple images of the same quasar arranged in a ring or arc pattern around the lensing galaxy. These Einstein rings are beautiful and scientifically invaluable for measuring galaxy masses, but they also unmistakably demonstrate that light paths aren't straight. The simple parsec definition assumes flat space and straight light paths, neither of which holds when light from very distant objects traverses regions of significant space-time curvature. You can still define distances, but you need to specify what you mean more carefully, as distance in curved space-time is inherently ambiguous, with different definitions yielding different answers. Cosmic expansion adds even more layers of complexity. When you observe a distant galaxy billions of parsecs away, you're seeing light that left that galaxy billions of years ago. During the immense time that light travelled toward Earth space itself was expanding. The galaxy has moved farther away during light's journey, and the expansion has stretched the wavelength of the light, creating the redshift we observe. So what exactly do we mean by the distance to that galaxy? Do we mean how far away it was when the light was emitted? That's look-back distance or light travel distance. Do we mean how far away it is right now at this very moment? That's proper distance, but it's not directly measurable because we can't see the galaxy as it is now. Do we mean its coordinate distance in a framework that expands with the universe? That's co-moving distance. Cosmologists actually use 3 different distance definitions, all of which legitimately deserve to be called distance, but which yield different numerical answers for the same object. Co-moving distance is the galaxy's separation from Earth in a coordinate system that expands along with the universe. Imagine a grid painted on space that stretches as space expands. Co-moving distance measures separation in that expanding grid. It's useful for describing the underlying geometry of the universe because it factors out expansion. Proper distance is what you'd measure if you could freeze the universe at a specific moment and lay meter sticks through space from here to the galaxy. For the current moment, this gives the galaxy separation right now, but for distant galaxies, we can't actually measure this directly because we see them as they were in the past, not as they are now. We have to calculate proper distance using cosmological models. Light travel distance, also called look-back distance, is how far the light actually travelled to reach us, which directly relates to look-back time. If light travelled for 10 billion years, it covered about 3 billion parsecs, or 10 billion light years. This is closest to what most people intuitively think of as distance, but it's less useful for cosmological calculations. For nearby objects within a few tens of megaparsecs, these 3 distances are essentially equal. The universe hasn't expanded significantly over the relatively short light travel time involved. But for very distant galaxies at redshifts greater than 1, they can differ by factors of 2 or more. A galaxy we see as it was 10 billion years ago might have a light travel distance of 10 billion light years, but a current proper distance of perhaps 18 billion light years, because space has expanded so much. Astronomers often use co-moving distances when discussing large-scale structure, because that removes the expansion effect and shows the underlying cosmic geometry more clearly when mapping the distribution of galaxies across cosmic time. Co-moving coordinates make patterns easier to see, but different subfields favour different conventions, and you always need to check which distance definition is being used in any particular paper or data set. This complexity has led some cosmologists to argue that we should simply stop reporting distances for very distant objects and instead report redshifts directly. Redshift is what we actually measure from observations. When you observe a galaxy's spectrum, you see familiar patterns of absorption or emission lines from hydrogen, oxygen, and other elements. But these lines appear at longer Radarr wavelengths compared to laboratory measurements of the same transitions. This redshift comes primarily from cosmic expansion stretching light waves as they travel. Measure a galaxy's spectrum, identify the spectral lines. By their characteristic patterns, calculate how much they're shifted compared to their rest wavelengths, and you have the redshift. That's the raw observable. It's what we can measure directly without any assumptions about cosmology or how distances relate to expansion. Converting redshift to distance, however, requires plugging the redshift into models of cosmic expansion that depend on assumptions about the universe's matter density, dark energy properties, curvature, and expansion history. Different assumptions yield different distances for the same redshift. A galaxy reported as 10 gigaparsecs distant in a 1990 paper might be listed as 11 gigaparsecs in a 2025 paper, not because we made new observations of that galaxy, but because we've refined our cosmological parameters. Our best fit values for the Hubble, constant matter density and dark energy density have changed, so our distance redshift conversion changed. The redshift itself hasn't changed, only our interpretation has. This argument for reporting redshifts has genuine merit. Redshifts are model-independent observables, whereas distances require model-dependent interpretations. But the argument hasn't won the day. Most astronomers still prefer converting redshifts to distances and reporting distances in parsecs or megaparsecs, even for very distant objects that require significant cosmological modelling to interpret. The distances feel more intuitive and concrete than redshifts, even if they are in fact more model-dependent. Saying a galaxy is 3 gigaparsecs away gives people a sense of its vastness in a way that saying it has a redshift of 0.7 doesn't. This preference for distance over redshift persists despite the theoretical arguments for preferring redshifts. The parsec also creates practical barriers when astronomers need to collaborate with physicists, engineers, or computer scientists from other fields. These fields overwhelmingly use SI units, the International System of Units, based on meters, kilograms, and seconds. Physicists think in meters, engineers design in meters. Computer algorithms expect inputs in standard units. Every interface between astronomy and these other fields requires careful unit conversion. Every physical constant needs to exist in both SI and astronomical versions. Every dataset needs careful unit tracking. This creates inefficiency and numerous opportunities for errors. Consider gravitational wave astronomy one of the most exciting developments of the past decade. The LIGO and Virgo detectors measure ripples in space-time caused by colliding black holes or neutron stars. These detectors are sensitive enough to measure space-time distortions smaller than the width of a proton. When black holes collide billions of parsecs away, the gravitational waves that reach Earth compress and stretch space by about 1 part in 10 to the 21st, power and almost unfathomable precision. This field brings together observational astronomers who study the electromagnetic counterparts of gravitational wave events, theoretical physicists who model the gravitational wave signals using general relativity, experimental physicists who operate the detectors, and computer scientists running massive data analysis algorithms searching for signals in noisy data. Physicists modelling the gravitational wave signals work in SI units, because the equations of general relativity are naturally expressed in meters and seconds. Their numerical simulations track black holes orbiting and merging, outputting gravitational wave amplitudes as functions of time. These calculations yield distances in meters from the observed wave amplitude and frequency. But astronomers analysing the host galaxies and electromagnetic counterparts expect distances in megaparsecs. When a neutron star merger produces both gravitational waves and a gamma-ray burst, astronomers want to know what galaxy it occurred in and how far away that galaxy is. They think in megaparsecs, because that's what their galaxy catalogues use. Computer scientists building the data processing pipelines need to convert back and forth. Constantly, gravitational wave amplitude gives distance in meters, convert to megaparsecs for astronomical context. Galaxy redshift gives distance in megaparsecs, convert to meters for gravitational wave analysis. Every conversion is a potential source of errors. Similar issues arise in planetary science where distances within the solar system are often expressed in astronomical units, but sometimes in kilometers depending on context. Mission design for space probes needs distances in kilometers because that's what navigation software expects. But orbital dynamics calculations sometimes use AU for convenience. In astrobiology, when discussing potentially habitable exoplanets, do you report distances in parsecs or light years? Scientific papers use parsecs, popular articles use light years, and press releases often need to include both. The most famous unit conversion error in space history was the Mars Climate Orbiter disaster in 1999. The spacecraft was tragically lost because one piece of software developed by Lockheed Martin generated thrust data in pound force seconds an imperial unit. Another piece of software developed by NASA expected Newton seconds an SI unit. Nobody caught the discrepancy during testing. The spacecraft's trajectory calculations were wrong by a factor of about 4.4. Instead of entering orbit safely, it passed too close to Mars and burned up in the atmosphere. $327 million lost to a unit conversion error. That's an extreme example, but it vividly illustrates the very real dangers of working with multiple unit systems. Every interface between systems is a potential failure point. The more unit conversions required, the more opportunities for errors. Teaching the Parsec to students presents its own set of challenges which paradoxically perpetuate the unit's use despite its unintuitive nature. To understand what a Parsec is and why it's defined the way it is, students need to grasp several prerequisite concepts. They must understand arcseconds as angular measurements, which requires understanding degrees and their subdivisions. They need to comprehend astronomical units and how we measure solar system distances. Crucially, they need to grasp parallax geometry and basic trigonometry. For a student taking an introductory astronomy course to fulfill a general education requirement, this represents a substantial time investment. These students often struggle with spatial reasoning and visualizing geometric relationships. Drawing triangles with Earth's orbit as the base and distant stars as vertices doesn't come naturally to everyone. The concept of measuring tiny angular shifts and converting those to distances requires a mathematical sophistication that not all students bring to an introductory course. That precious class time could instead be used to cover topics students might find more immediately engaging and memorable: exoplanets, and the search for life beyond Earth, black holes, and the bizarre physics within the Big Bang, and how we know the universe had a beginning or stellar evolution, and why the sun will eventually become a red giant. These topics don't inherently require understanding specialized distance units. The student can learn about the discovery of planets around other stars without needing to know those stars' distances in parsecs versus light years. Light years are far more accessible for teaching. Students already understand what a year is, and they know light is incredibly fast. The concept of the distance light travels in a year makes immediate intuitive sense. You can teach the scale of the universe using light years without needing extensive mathematical prerequisites. Say, Alpha Centauri is 4.2 light years away, and students instantly grasp that it's far and that we're seeing it as it was 4 years ago. No geometric diagrams needed. But here's the educational dilemma: as long as professional research papers continue to use Parsec, students aspiring to careers in astronomy must learn them. They need to read research papers as undergraduates to prepare for graduate school, and those papers will invariably report distances in parsecs, kiloparsecs, or megaparsecs. Students need to understand what those numbers mean and how to work with them fluently, developing an intuition for whether a claimed distance makes sense given other properties of an object. So introductory astronomy courses end up teaching both units, light years, for the general education students who won't continue in the field, and parsecs for the majors and anyone planning to read professional astronomy literature. This dual instruction takes more time than teaching just one unit would require. It's inefficient but deemed necessary given the professional populace split in unit preference. Upper-level undergraduate courses and graduate courses teach exclusively in parsecs, because that's what students will encounter in research. Every catalogue they consult, every paper they read, every talk they attend at conferences will use parsecs. Learning to think in parsecs becomes a fundamental part of professional socialization. It's joining the community of astronomers. This educational system perpetuates the unit through generations. Professors learned parsecs in their training, internalized the unit, developed intuition for it, and came to think naturally in those terms. So they teach parsecs to their students, who become the next generation of professors, teaching parsecs to their students. The cycle continues independently of whether parsecs are objectively the best choice. They're what the profession uses, so they're what gets taught. Several major observatories planned for the 2030s will shape astronomy for the next several decades, and all of them will further entrench the parsec through their data products and analysis software. The extremely large telescope ELT, being built by the European Southern Observatory in Chile's Atacama Desert, will boast a primary mirror 39 meters in diameter, over 128 feet. It will be the largest optical telescope in the world when completed at a cost exceeding €1 billion, with first light expected around 2027. The ELT will study exoplanet atmospheres in unprecedented detail, potentially detecting biosignatures. It will observe the most distant galaxies in the universe, seeing them as they were when the universe was young. It will study dark matter and dark energy. and it will track stars orbiting Sagittarius A, the supermassive black hole at our galaxy's centre. All of this groundbreaking science will produce distances in parsecs, because that's what the astronomers designing the instruments and planning the observations expect. The Nancy Grace Roman Space Telescope, formerly known as FIRST, is NASA's next major space observatory after James Webb. Named after NASA's first chief astronomer, it's designed for wide-field surveys and will revolutionize studies of dark-energy exoplanets through gravitational microlensing and galactic structure. Launch is currently planned for May 2027, with total mission cost exceeding $3.9 billion. Roman will survey huge areas of the sky, cataloguing billions of stars and galaxies. It will measure distances to nearby galaxies through Cepheid variables and Type Ia supernovae refining measurements of the Hubble constant. It will map the three-dimensional distribution of dark matter through weak gravitational lensing. Every distance measurement will be in parsecs, because that's what the data processing pipelines output and what astronomical databases expect. The Square Kilometre Array (SKA) is an international radio telescope project that will eventually boast a collecting area of 1 square kilometre, spread across thousands of individual antennas in Australia and South Africa. It will be the most sensitive radio telescope ever built by several orders of magnitude. The first phase, SKA Low in Australia, operating at low radio frequencies, and SKA Mid in South Africa at higher frequencies, should be operational in the early 2030s. SKA will study the cosmic dawn, the period when the first stars formed in the early universe. It will detect radio pulses with exquisite timing precision, using them to search for gravitational waves. It will map neutral hydrogen across the universe, tracing cosmic structure evolution. It will even search for radio techno signatures from advanced civilizations. All of these programs will involve distance measurements in parsecs. All of these observatories, according to current plans, will use parsecs for their primary data products. The science teams designing these instruments and planning observations are professional astronomers who think in parsecs. The data processing pipelines being developed assume parsec units as defaults. The archive systems being built will store distances in parsecs. These are multi-billion-dollar, multi-decade projects that will produce data for 50 years or more. Their design decisions will influence astronomy well into the second half of the 21st century. Simply through continued use in flagship missions, the parsec will remain entrenched. Each new catalogue adds to the accumulation of parsec-based data. Each new survey builds on previous surveys' distance scales. The infrastructure grows and hardens. Switching becomes progressively more difficult as more depends on the existing system. But countervailing forces exist that might eventually shift practice toward more accessible units. Astronomy is becoming increasingly data-driven and interdisciplinary. Modern surveys produce datasets so vast that individual astronomers cannot analyse them alone. Collaborations span many fields, bringing together experts in physics, statistics, computer science, machine learning, and various domain-specific areas. If climate scientists wish to use astronomical data to understand solar variability's effects on Earth's climate over geological timescales, they shouldn't need to learn specialised astronomical units first. The data should be accessible in familiar units. If geologists want to compare impact crater ages to supernova rates that might have caused extinction events, converting between parsecs and familiar distance units shouldn't be a barrier to entry. Open science movements emphasise making data accessible beyond the immediate research community that generated it. Data should be fair, findable, accessible, interoperable, and reusable. Requiring specialised unit knowledge to interpret data works against these goals. Parsecs, even if a small one, are a barrier to interdisciplinary research. When we eventually detect biosignatures in an exoplanet's atmosphere confirming life beyond Earth, the distance to that planet will become one of the most discussed numbers in human history. Media coverage will be overwhelming. Every news outlet worldwide will report the discovery. Every person on Earth will hear about it, and they will almost certainly give the distance in light years not parsecs, because that's what general audiences can understand. Imagine the headlines, "Life found on planet 40 light-years away." This resonates with people. They understand that light from that planet takes 40 years to reach Earth. They grasp the timescales involved. Life found on planet 12.3 parsecs away sounds technical and alienating. It requires explanation that most news articles won't provide. This might create pressure for astronomers to standardize on light years for public-facing work, or at minimum to always provide both units in press releases and papers intended for broad audiences. If every press release has to convert from parsecs to light years anyway for public comprehension, why not provide light years directly in the scientific papers as well? Similarly, if we ever reach the point of seriously planning interstellar missions, perhaps using breakthrough technologies like nuclear pulse propulsion, laser-pushed light sails or fusion rockets, all discussion of those missions will naturally use light years. A mission to Alpha Centauri, CIRCE-4, 4 light-years away, immediately tells you that light-speed travel would take 4.124 years. The travel time and distance have obvious connections. At 10% of light speed, which might be achievable with advanced propulsion, the trip would take 42 years. At 20% of light speed, 21 years. These calculations are straightforward when using light years. With parsecs, you'd need to perform conversions to understand timescales. Alpha Centauri at 1.3 parsecs requires mentally converting to light years before you can assess travel times at various speeds. The most likely future in my assessment is that parsecs will remain dominant in professional astronomy for the foreseeable future, but software tools will make the choice of units less important practically. Modern astronomical databases don't just store numbers, they store numbers with rich metadata indicating units, precision measurement method and provenance. Query a database for a galaxy's distance, specify what units you want in the output, and the system converts automatically. This capability already exists in many systems. The Simbad astronomical database maintained by the Strasbourg Astronomical Data Center stores distances primarily in parsecs, but can display them in light years on request. The NASA Exoplanet Archive provides distances in both parsecs and light years by default. These are proofs of concept showing that multi-unit support is technically straightforward. This functionality just needs to become more universal and user-friendly. Every major astronomical database and analysis tool should support seamless unit conversion. Users should be able to set preferences once and have everything display in their preferred units, automatically with no manual conversion required. Machine learning algorithms are increasingly used to analyze astronomical data, discovering patterns humans might miss. Adding intelligent unit conversion to these systems is straightforward. The algorithms don't care whether inputs are in parsecs, light years, or meters. They work with numbers. Humans care about units because we need to interpret the numbers, but software can handle conversions invisibly. Systems could even learn individual users' preferences through usage patterns. If an astronomer always queries distances and immediately converts to parsecs, the system learns to provide parsecs by default for that user. If a science communicator always converts to light years, provide light years. If a physicist working on gravitational waves wants meters, provide meters. Adaptive interfaces that learn user preferences already exist in other contexts. Applying this to astronomical unit conversion is a natural progression. This doesn't resolve the fundamental question of which unit is objectively better or more natural. Different communities will always have different preferences based on their needs and training, but it makes the question less important in practice. The parsec can remain astronomy's native unit while becoming less of a barrier to outsiders, because translation will be seamless and automatic. The main blocker to changing units isn't technical capability, we have the technology to convert between units easily. The blocker is social and institutional. Individual astronomers have little incentive to deviate from standard practice. If you submit a paper reporting distances in light years or meters, when everyone else uses parsecs, reviewers might flag it as non-standard. They might request you convert to parsecs before publication. Using non-standard units marks you as an outsider, or someone who doesn't understand field conventions. Database managers might hesitate to ingest your data, if it uses non-standard units, as they'd need to verify the units are correctly flagged in metadata and ensure conversion factors are applied correctly. It's simply easier to require standard units than to handle multiple possibilities. So databases often specify required units, and parsecs are what they require. This is a classic collective action problem from economics and sociology. Everyone might benefit if everyone switched to a more accessible or universal unit like light years or meters, but nobody wants to be the first to switch, because doing so creates individual costs through friction with existing infrastructure and norms. The group would benefit from coordination, but individuals are punished for deviating unilaterally. There have been some attempts at coordination to address this. Some journals have discussed requiring papers to report distances in both parsecs and light years, providing professional and popular units simultaneously. This would make papers more accessible to broader audiences while still serving professional needs. But implementation has been inconsistent. Some journals adopted this recommendation, others didn't. Without universal adoption, the impact is limited. Some databases added options to output distances in multiple units on request. The Sloan Digital Sky Survey, one of the most comprehensive galaxy surveys ever conducted, provides distances in both parsecs and light years in many of its data products. The Gaia archive allows users to choose output units for many parameters. These are positive steps toward better accessibility. But these efforts have been piecemeal. They haven't fundamentally changed professional practice. Astronomers still write papers primarily in parsecs. They still think in parsecs when doing research. They still present conference talks using parsecs. The infrastructure accommodates alternatives in some places, but the default remains parsecs. The International Astronomical Union could theoretically mandate a change through an official resolution. They are the body that makes formal decisions about astronomical nomenclature, coordinate systems, time standards, and unit definitions. They could decree that all astronomical publications must report distances in both parsecs and light years, or that light years should become the primary unit with parsecs as secondary. But the IAU generally prefers letting practice evolve organically rather than imposing top-down changes. They recognise that mandating changes that the community isn't ready for breeds resentment and is likely to be ignored. Scientific communities are difficult to steer by fiat. Change works better when it emerges from consensus. And organically, practice hasn't evolved toward abandoning parsecs. If anything, Gaia has strengthened parsec dominance by producing a massive parsec-based catalogue that everyone uses. The scientific literature continues to use parsecs almost exclusively. Conference talks use parsecs. Grant proposals use parsecs. The status quo persists. My prediction for 50 years from now is that the parsec will remain the dominant unit in professional astronomy, but with significantly better software infrastructure, making the choice of units far less constraining. Major surveys launching in the next decade, like the Vera C. Rubin Observatory's Legacy Survey of Space and Time LSST, starting in 2025, will produce parsec-based data. LSST will survey the entire visible sky every few nights for 10 years, cataloguing billions of objects and tracking anything that changes. All distances will be in parsecs. That data will be analysed and reanalysed for decades. By mid-century, we'll have another generation of parsec-based data accumulated on top of Gaia, on top of Sloan, on top of the hundreds of earlier surveys. The accumulated infrastructure of parsec-based catalogues will be even larger and more entrenched than today. But simultaneously, better software infrastructure will make units more transparent to users. Data visualization tools will seamlessly convert between units. Analysis pipelines will accept inputs in any reasonable unit and convert as needed. Machine learning systems will learn user preferences. The parsec will remain astronomy's native unit, but become less of a barrier to entry because translation will be automatic and invisible. Young astronomers entering the field in 2075 will probably still learn parsecs as part of their training. Graduate programs will teach parsecs because that's what the literature uses. They'll use parsecs in their professional work writing papers and giving talks. They'll barely question whether alternatives might be better, because the infrastructure they inherit will be built around parsecs. But those same young astronomers will also have tools that previous generations lacked. They'll work with data systems that handle unit conversion transparently. They'll collaborate with researchers from other fields without unit barriers. They'll communicate with the public using light years without thinking about it. The Parsec will be their professional language, but not an exclusive one. Fields develop their specialized conventions and terminology for good reasons. These conventions encode accumulated wisdom and make communication within the field more efficient. Learning those conventions is part of joining the field and becoming fluent in its discourse. Particle physics has its electron volts for energy bands for cross-sections and inverse femtobarns for integrated luminosity. Nuclear physics has its becquerels for radioactivity and grays for absorbed radiation dose. Astronomy has its parsecs for distance. These specialized units often seem arbitrary to outsiders. Why measure energy in electron volts instead of joules? Why measure cross-sections in barns where one barn equals 10 to 28 square meters? The answers involve historical accident and practical convenience similar to the parsec. But these units serve their communities well by making common calculations simpler and by creating a shared precise language. The parsec emerged from Friedrich Wilhelm Bessel's landmark 1838 measurement of stellar parallax to 61 Cygni. It proved immediately useful for parallax work because of its geometric simplicity and direct relationship to measured angles. It became the standard unit across all of astronomy through a combination of genuine utility for working astronomers and historical momentum as the field grew. It persists today despite its recognized limitations and arbitrary roots, because changing it would require a monumental coordinated effort across the entire global astronomy community. Databases would need updating, software would need rewriting, textbooks would need revising, papers would need to be written differently, astronomers would need to retrain their intuitions ingrained over decades. The costs of such a change are substantial and concentrated on those doing the changing, while the benefits are diffuse and uncertain. Is the parsec optimal? Number a unit based on human angular measurement conventions and marking. No natural cosmic boundary is clearly arbitrary in deep ways. Is it good enough? Clearly yes, since the field continues to function well and make rapid progress using it. Astronomy has never been more productive than it is today, and that productivity isn't demonstrably limited by the choice of distance units. The parsec story reveals how arbitrary choices made for good reasons in particular historical contexts can become entrenched standards that shape practice for centuries. It shows how historical momentum and infrastructure investment create profound resistance to change even when intellectually superior or more accessible alternatives might exist. It demonstrates how social factors matter as much as if not more than purely technical factors in determining scientific practice. This pattern appears everywhere in human endeavours, not just in science. Languages contain arbitrary grammatical features and irregular verbs that persist, because changing them requires coordinating millions of speakers. Technology standards like the QWERTY keyboard layout or the width of railroad tracks often reflect early design choices rather than optimal solutions discovered later. Legal systems carry historical precedents and procedural rules that made sense in past contexts but persist into changed circumstances. Academic institutions maintain tenure systems and departmental structures reflecting 19th century university organisation. Every time you see an astronomical distance reported in parsecs, you're witnessing this grand silent process in action. You're seeing the echo of an 1838 measurement technique. You're seeing the accumulated practice from nearly 2 centuries of astronomers all using the same unit. You're seeing the peculiar path by which one particular angular choice became foundational to an entire scientific field. Behind every measurement, every scientific paper, every physical theory, there are humans making choices. Sometimes those choices are brilliant insights that transform understanding. Newton choosing to analyse forces and accelerations rather than speeds, Einstein choosing to make the speed of light constant and let time be relative, Hubble choosing to study Cepheids and nebulae to measure their distances. Sometimes choices are arbitrary decisions about conventions that happen to stick the choice to divide circles into 360 degrees, the choice to define 1 arcsecond as 1/3600th of a degree, the choice to base a distance unit on 1 arcsecond of parallax. And sometimes choices are just whatever turned out to be convenient at the time and never got seriously re-examined using parsecs, because that's what parallax measurements naturally produce. Continuing with parsecs because that's what existing catalogues use. Teaching parsecs because that's what research papers report. The parsec is all three simultaneously. It was a clever choice for parallax work, elegant in its geometric simplicity. It was an arbitrary choice in that 1 arcsecond has no physical significance, just historical accident. And it was convenient enough that nobody saw sufficient reason to change once institutional infrastructure grew around it. When you look up at the night sky on a clear evening, those stars are separated by distances measured in parsecs by professional astronomers. Not because parsecs are the best possible unit by some objective measure, but because they're established and the costs of switching are high, while the benefits remain unclear. Proxima Centauri sits 1.302 parsecs away. Sirius sits 2.64 parsecs away. Betelgeuse sits somewhere around 170 parsecs away, though uncertainty remains. The galactic centre sits about 8.2 kiloparsecs away. Andromeda sits 0.78 megaparsecs away. These numbers tell stories of light travelling for years across incomprehensible emptiness. Stories of stellar birth in collapsing gas clouds, stellar evolution through nuclear fusion stages, and stellar death in planetary nebulae or supernova explosions. Stories of galaxies colliding over hundreds of millions of years of supermassive black holes, growing of cosmic expansion carrying everything apart. And stories of humans trying to measure and understand it all, using whatever tools and units we developed along the way. The parsec is one of those tools. Strange to outsiders, yes. Unintuitive to anyone not trained in astronomy, absolutely. But familiar and functional for those who use it every day. Science is ultimately a human endeavour, done by people working in communities with shared training language and practices. Social and psychological factors matter as much as pure physics or mathematics in determining how science gets done. Communities develop shared language and conventions that reinforce group identity and smooth collaboration within the group, even if those same conventions create barriers to outsiders. Perhaps having field-specific traditions and units serves valuable purposes beyond pure efficiency. Maybe the parsec, precisely because it requires explanation and training to understand, helps define who's part of the professional astronomy community. Maybe there's value in maintaining some specialised knowledge that marks expertise and signals membership in the community of practice. Understanding this makes us better, more sophisticated consumers of science. When we read that scientists disagree about something, or that different fields use different approaches to the same problem, we shouldn't always assume it's because the facts are uncertain or the scientists are confused. Sometimes it's because conventions differ across communities, standards vary between fields, or definitions aren't universal across all contexts. This doesn't mean science is arbitrary or unreliable. It means science is done by humans embedded in social structures with histories and traditions. Understanding this also gives us more realistic expectations about scientific progress and change. Progress doesn't happen just because someone has a better idea or because new evidence emerges that invalidates old theories. Change happens when communities collectively decide to adopt new practices, when institutions invest resources in new infrastructure, when enough people conclude that the benefits of changing outweigh the costs, and that coordination problems can be solved. That's fundamentally a social process, not just a scientific or technical one. It involves persuasion and argument coordination across many actors, political skill in building coalitions, and a willingness to invest resources in transitions whose payoffs might not be immediate. The parsec's persistence over nearly 2 centuries demonstrates how powerful these social and institutional factors can be in maintaining the status quo. Thank you for spending this time exploring the strange story of the Parsec. If this changed how you think about scientific standards, about how science actually works as a human endeavour, about the ways history and social factors shape current practice, then the time was well spent. Keep looking up at those stars scattered across the night sky. They're not going anywhere, at least not on human timescales. And whether we measure their distances in parsecs, light years, astronomical units, meters, or some future unit we haven't invented yet, their light has travelled across the cosmos to reach us. That remains profound and worthy of wonder no matter what units we choose to describe it. Good night.